Welcome to Study Loop.
This is question 2832, and we have a kind of interesting situation here. We have one long horizontal wire AB, and that's on the surface of a table. And then we have this other wire CD that is sitting vertically above, but can slide up and down on these little metal guides. And we want to figure out the equilibrium height H that the wire CD is going to rise, assuming that the magnetic force on it is completely due to the lower wire here. So what we want to do is set up a force diagram here. So we're going to consider a point on this wire. We have a force. Notice that these currents are in opposite directions, which means that the force between them is going to be a repulsive force. So this bottom wire is going to repel the top wire, causing a force up. And then the force down on it is going to be gravity. So we know that the force of gravity is equal to mg, where m is the mass and g is 9.8 meters per second squared. That's the force of gravity. Now at equilibrium, these forces are going to balance. So we want these two forces to cancel out and equal 0. So first let's take a look at this force, the magnetic force from the bottom wire. So here's the general expression for the force exerted on a wire, on another wire. So notice here that we have I1 and I2 are both equal to I, since their magnitudes are the same. So we can just substitute this in with I squared. And then the distance r that's going to be separated by the two of them, this is going to be ultimately at equilibrium. It's going to be our height h that we want. So we're going to try to eventually solve for h, but this is what we want. Now we want to just get f by itself, so let's bring over the factor of L, multiply by L on both sides, and bring that in over here. So now let's consider, we know that the force of gravity is mg, but we don't know what the mass is. So in the question, we're told that the mass per unit length of the wire is lambda. So we're told the mass per unit length, but we're not told the actual mass itself. So to get the mass, what we want to do is multiply lambda times the length of the wire. So the length of our wire is going to be L, and that will give us the total mass, because mass per unit length times the lengths will cancel out, giving us just the mass. So our force of gravity here then will be mg, which is just going to be lambda times L times g. And again, g, I'll just write explicitly here, 9.8 meters per second squared. So now we want to set these forces equal, because we want basically F to equal mg. That will give us our equilibrium condition here. So let's set our force here equal to lambda times L times g. And we want to simplify this a bit so we can see that there's a factor of L in both sides. So those are going to cancel, which is good because we weren't told what L was in the problem. And we want to get h by itself. So let's multiply both sides by h here. And then we want to divide by lambda and g, because we want to get h by itself. So let's pull those in the denominator. So finally, we're going to get that h is equal to mu naught I squared over 2 pi lambda g.